Will there be? Yes, we're going to do that. Quantum, not, I don't know about Fisher information, but we're going to discuss some quantum information probably soon. Okay. Any other questions? But again, this course is, you know, it's only a 10-day course. So, and we have people coming from various backgrounds. And so it's very hard to do an exhaustive coverage. But what we do hope is that you got the necessary tools to go investigate that yourself, like the quantum Fisher information or whatever you would like to do, that you have the necessary introduction to quantum mechanics, Qiskit, and things like that, that enable you to research into other topics deeper. And there are lots of resources to do that. The only resource that one needs is time, I guess. Are there any other questions? Okay. Please enter your name for attendance. Anuradha, you asked something. You mean online open course books? Yes, there are a lot of online open courseware. For example, MIT Open Courseware, Stanford, even IBM has a lot of resources. Yeah, there are a lot of open course resources. Yes. Also, there are papers as well. Some papers that you can find, like um, the references that we put in here in some of the lectures. You could use those. So there are so many open resources like that. Okay, I'm going to close the poll. I hope everybody entered their name. Okay, let's get back to where we were and see what we were discussing. So I hope you were able to understand how to measure fidelity and what that means. So the take-home message is fidelity is what we designed it, is we designed fidelity as a scalar quantity. That is, it's a trace of something, so it remains the same irrespective of the basis. And we have in general a mixed state that would be outcome of whatever preparation or gate measurement. And we cannot really distinguish between what is what. And even the state preparation could look like error. And we cannot tell really the difference between the gate, the state relaxation, and all that. And then we saw how to measure this fidelity on like a single quantum state. If I am preparing a pure state like psi 0, I can do this, right? And then we also saw for other ones where these kind of things usually give you only the diagonal elements P0, P1, but we also saw other gates where we needed to compute C. So for doing such things, so the matrix being P0, P1, CC star, right? We also needed to compute off-diagonal elements. And in such cases, when we are computing off-diagonal elements, then what we saw was that we needed to apply more gates. And so that itself could lead to more error, right? So that's what we have seen. And so now let's talk about measurement errors and misclassification, right? So ideal measurement, when you measure 0, you get 0, 1, you get 1, right? Misclassification, that is just in readout. That is, let us say I have some state preparation, then I got this to be, it is preparing identically prepared particles that would yield the same result. But let's say you measure and you find 1 with probability beta instead of 0, right? And if it prepared 1, you're supposed to find 1, but you find 0 with a probability of alpha. right? Then we say that, these are basically hardware, calibration, readout, all these errors that are combined. For example, you're in your microwave resonator, your readout resonator, the circuit itself is leading to this. So we model this using a confusion matrix, and this confusion matrix is defined as this, right? So if you get one with a probability of beta, that means you get the true probability for one. For zero would be 1 minus beta, and that's what you see as the first matrix element, which is you prepared zero truly and you measured zero truly. That is 1 minus beta. You prepared one truly and you measured this one as, so 1 minus alpha. So this alpha and beta would be off diagonal elements in the matrix M. So that's why we call those as the confusion elements. That is, ideally they should be zero, right? Because if you're making zero, you should measure zero. If you're making one, you should measure one. So ideally alpha and beta should be zero, right? But they are not. So Mij is the probability of measuring I when the true state is J, right? So you don't want the off diagonal elements. So if the probability is, if there is high fidelity, right, then these are 0.01, 0.02, like that. And we can sort of say that the measured probabilities are the matrix, the confusion matrix times the true probability, because the off diagonal elements would adjust for what the true probabilities are. Any questions on that? So many times you may see the confusion matrix being mentioned, and that's what it means. The off diagonal elements are measuring probability of measuring I when the true state is J. So if you have a multi-qubit, so far we looked at single qubit. If you have multi-qubit, then basically your confusion matrix would be a direct product of n qubits, right? And so the measured probability would be n of these this direct product on the true one, right? So so this is how the error mitigation is done. That is, you sort of calibrate for M based on known basis states, and you apply its inverse. So what it is saying is that you can somehow make measurements, model this confusion matrix through some quantum channel, which we will discuss, and then apply the inverse of it. So you can reduce the measurement error. So those are the error mitigation or the error correction steps, right? So this typical mitigation improves the fidelity by only a little bit, right? But not by so much, 1 to 2%, right? So this is where the noisy quantum hardware and software design becomes important. So as long as we have errors in the quantum hardware, right? We need to develop algorithms that account for this noisy hardware. And this noise can arise from multiple reasons, right? And it could be platform specific, meaning for a superconducting qubit, it could be one way. And for n qubits, for 100 qubits, it may be one way. For 50 qubits, it may be another way, right? So understanding what these patterns are and how to model these noise patterns is very, very important for error mitigation, error correction, and things like that. And also, like, you do not want to keep doing every measurement directly on real QPU, because the QPU time is very expensive. It's all in a dilution refrigerator, which is very expensive to maintain, right? And so if we can make better simulators which can encode for this noise, then we can simulate before we run on the real QPU. We could simulate, make sure that we get what it is, and then we can compare it with a real quantum computer. So so what we would like to do is develop accurate noise models. That is the best alternative for us to ensure that we can test algorithms in various noisy scenarios. And this also becomes important for quantum information. For example, when we are exchanging information, right? Both people are not in same place, or you are in different locations, and this needs to be sent on a secure channel to someone. And so as the information is going, it takes time from one channel to another channel, one place to another place. And so it can, be affected by noise, right? So these noise models even become very important there in terms of understanding information itself, right? And then what we have so far done is like, few measurements, like one or two measurements. But now let us say you want to compute, you want to do like a long computation. So in classical computation, I could do long computation. Technically, I can do as long as I want in some sense. But you cannot do computations for an arbitrarily long time on quantum computer, because then your decoherence is going to come into picture. So your decoherence time is around 10 microseconds. So on each qubit, you could do probably within like 10% of the time, like within 1 or 2 microseconds. So you cannot perform a lot of long computational things. Like, for example, one of the things that quantum computing is expected to be useful, which I hope we will get a chance to discuss, is factorization of large numbers. And that takes time, right? It increases exponentially as the number increases. So you want to be able to do the computation for a long time. But as you're trying to do for a long time, you need to have good models that would account for the noise. And so you need to know quantum error correction, for which we need to model the noise. And this is why we need to understand and make quantum channels. And that's the topic of our next discussion. So quantum channels are necessary for multiple things, for basically modeling the noise. And that noise can come into picture anytime there is long computation, exchange of information, all sorts of things like that. So we're going to talk about the general picture of quantum channels. We're going to look at a couple of specific channels and begin to understand quantum information. So today we will begin with the basics of quantum channels. Before I proceed, are there any questions on what we discussed in the first lecture? Yeah, no questions? Okay, I wish you had more questions. So let's see. So now to introduce quantum information and quantum channels, let's begin with just classical information, right? So here we're going to set up this classical communication. We're just going to see, okay, there's some question. There are so many courses, then how would you find the right one? Hit and trial. Okay. I made okay, Anuradha, that you have to hit and trial, not that way, but you can look at resources like Nielsen and Chung, the standard textbooks, and IBM, and go through those. I wouldn't say hit and trial. I mean, there are some standard ones, so I would first look them up and see which one is good, right? Okay, I hope that answers your question. Shwazirani is complete playlist and good import. Okay, so Saptagiri has some suggestion. Um, Thank you. So let's get back to this one. So let's see. You have Alice, who is the sender, right? And we have Bob, who is not with Alice. He's receiving the information, right? We make no assumption about physical nature of messages, right? And we describe everything using classical probabilities. So we're going to just do classical probability. So Alice can send, let's say, some sequence, right? And possible messages, right? She has, let's say, messages x1, x2, x3, so on and so forth, right, till xn. So this is a possible set of messages that she can send. And so the probability that she picks some message xj is given by pj, right? And these probabilities, of course, satisfy the summation, right? So the communication channel, which is between Alice and Bob, this can transmit n messages, one of n messages in each use, one of n per use. So it has some rate at which it communicates, right? And we often introduce somebody who is an eavesdropper called Eve, who may be tapping into the channel between Alice and Bob, right? And so Alice sends X1 to Xn one of the messages which she picks with probability Pj and sends it to Bob. And Bob receives one of the m possible messages, right? That could be Y1 to Ym, right? Or Ym to Yn, right? So then he gets it with the probability of Qj, let's say, right? So probabilities for Bob are denoted by Q, and probabilities for Alice are denoted by P, and there is a communication channel. So this communication channel, the ideal communication channel would be that whatever Alice sends, that is, if Alice, let's say Alice sends 1001, then ideal communication channel doesn't disturb anything, and Bob gets 1001, right? That would be the ideal communication channel. But the communication channels are not ideal. They would involve, let's say it's a fiber optic cable, right? Something like that. And so if I send some pulses, then there could be some sort of disturbance or some sort of change in what the person is going to receive, right? So as we said, the information is in a message that Alice is going to send is the number of bits required to describe X. So whatever this is, we're going to look at the number of bits that are required, minimum number of bits that are required to send that information. So you can compress this, and what it tells us is how many minimum bits do I need to get the perfect information from Alice to Bob, right? So we are going to quantify this. So to quantify that, we're going to introduce the concept of information entropy. So the measuring X, whatever Alice is going to send, when Alice picks, I do not know what she picks, right? Let's say you put yourself in the position of Bob. You don't know what Alice is going to pick. Let's say she picks some Xi, right? And then she sends it over, right? And then you actually make a measurement. And when you make a measurement, you perfectly know what she sent. Let's say you do not know, let's say you have only two choices. She can either send you 0 or 1, right? So before you receive it, you do not know whether she will send 0 or 1, right? And so there is entropy in whatever she is sending. But once you get it, let's say you measure it and you found it is 1. Again, we're talking only about classical bits here, no quantum yet. Once you find that it is definitely 1, then there is no more entropy, it is 0, right? So the entropy of the thing goes 0 and you get information. Reduction in uncertainty leads to information gain, right? After you get in classical, after you get the first measurement, repeated measurements will not give you any advantage, right? That is, once I measure it to be 1, if I keep measuring it again and again, then it is not going to give any new further information, because by measuring it, I have reduced the entropy already. And from that reduction in entropy, I gain whatever information that I need to gain, right? So we are going to start defining entropy formally. So if Alice can send, each message with a certain probability, then we define the information content using Shannon entropy, right? Using Shannon entropy, and this is related to sort of how you do count entropy in in statistical mechanics, right? It is related to a similar thing, but here we're talking about information content. Here, let's give it a symbol H of X, and where X is consisting of X1 to Xn, right? Messages. And so then we would say the information entropy is you go over 1 to n, right? And each of these has a probability P1 to Pn, right? So then we have Pj log Pj, right? That's how we define information content on this thing, right? So in general, h of x depends only on P and not on the content of the message itself. It only depends upon what is the likelihood of sending that particular message, not on the content of not on the labels exchange, right? If the event is PJ is 0 or PJ is 1, if you have 0 probability, then you don't contribute to the entropy because you're never going to be sent. That message is never going to be sent. That's what PJ0 means. But if you also have PJ is equal to 1, that is, you definitely know this is the message that is going to be sent, then that means there is no uncertainty. Whether the probability is 0 or probability is 1, there is no uncertainty there. That means there is no information to be gained. You know, definitely, certainly you know what it is. So in both cases, there is nothing new to learn. So the information entropy is in general between 0 to log n, where you have n bits, right? So let's see one example here. Let's say Alice can send 2 messages, 0 and 1, right? Again, these are classical bits. And she chooses 0 with probability p and 1 with probability 1 minus p, right? How much information does one message contain, right? So then, like we said, we just take this, right? So we have 2. So our x1, x2 is 0 and 1, right? And p1, p2, the probabilities are p and 1 minus p, right? So then our h of x would simply be negative p1 times log p1 plus p2 times log p2, right? So that would be minus p log p plus 1 minus p log p, log 1 minus p, right? Are you following me? Any questions? Okay. So then if we want to find the maximum information content, then what we could do is we can simply take a derivative of that, right, on that set with respect to the probabilities. And if you do that, you see that, you know, here you're going to get minus log 2p, and you can do the derivatives and set it to 0. And that gives you where you have the maximum entropy. That is, if I have 50%, 50% chance of sending these two, then I have the maximum uncertainty that time. When both are equally likely, I have maximum uncertainty. If it is anything other than that, like if I definitely know she is going to send 0, then the entropy is 0. If I definitely know Alice is going to send 1, then entropy is 0, right? But even if you consider 70-30 or 30-70, that also you have more definitive outcome for one than the other. Only when both of them have equal likelihood, you have maximum uncertainty, right? So your uncertainty, if I were to look at like, you know, as a function of, you know, p, right, it would look something like this, right? So this is your h, and this is your p, and this is where p is half, right? If p is 0, then the entropy is 0. If p is 1, the entropy is 0 again, right? So the maximum entropy would be at p is equal to half, right? So then, you know, when we say p max is half, right, what would be the entropy at p max, right? P max entropy would be, you can compute what that is. That will give you 1 bit, right? You can take half log 2 half and plug it into this, right? So it will give you 2 times that, and that will give you 1. So that means you have 1 bit of information in this, right? That is, if you perform a measurement on that, you can learn one bit of information. So that's how we interpret this entropy, that if both messages are sent with equal probability, then 1 bit is necessary to specify which message is sent, right? If Alice always sends the same message with p is equal to 0 or 1, right, then no information needs to be stored or transmitted because you know what she is going to send, right? For any other value of p in between 0 and 1, right, what we need is h of p gives you the average number of bits required to store or transmit the message, right? So a message can on average be compressed to h of x, whatever is the h, sometimes h of p or h of x, but h of x means the data set with probabilities p1 to pn. Same thing as h of p. that is the that is the minimum number of bits I need to convey whatever Alice is sending to Bob. Right? So I can compress the data maximum to h of x bits. I cannot compress below that. But here I'm assuming that the channel, recall that when we talked about Alice sending messages to Bob, we sort of considered the channel itself to be noiseless. So this is called channel's noiseless theorem, because we are not considering the channel to be having any noise at all, right? So now let's do another example to understand this better, right? So let's say Alice can send 3 messages, which could be A, B, C, with probability A being half, B and C being 1/4, right? How much information is contained in one message, right? Again, we do the same thing, right? We know that it is minus J, Pj, log Pj, right? And we have Pa to be half, Pb and Pc to be 1/4. So we can simply plug these values into that, and then you can compute half log half, and same thing here, and then you get 1.5 bits. So then that means I need at least 1.5 bits, that each message carries on average at least 1.5 bits of information, right? If all 3 messages were equally likely, then you reach the maximum entropy, which is 1.58, 1.6 bits, right? So I hope you're following that the entropy encodes for the number of bits that you have. So an optimal prefix-free code assigns that's like I want to send multiple messages, right? Then what we do is some messages are okay. There's a question, I think. So one necessary condition for Bob that he should at least know what all possible information Alice can send. Then only we can write h of x. Is it true? No, not really. So we don't need to know the. That is what I was saying, that we don't need to know the content of the message. We only are looking at for the. So when I say like the memory storage, for example, I have like these many bytes. What you want to store in those bytes is is another matter, right? So, but I require these many bytes to send this much information. That is based on, we are saying there are these many messages. So each message is this likely. We don't need to know the content of the message. So Bob doesn't need to know the content of the message. So we're only looking at the probabilities. So if you look at the entropy, we only need the probabilities. I don't need to know the messages x1, x2 itself. Does it answer your question, Subhanshu? Yeah. So the average length would be that whatever message is more probable, you want to use shorter bit strings for more probable messages, longer bit string for less probable ones. That is, let's say I have the same message that I want to send. We will do an example. Then for example, let's say in the previous example, we have 3 messages here, A, B, and C, right? We don't know the content, what A, B, and C are. Some messages. All we know is message A will be sent with probability half. That is, it is sent more number of times. Then what you want to do is, because it is sent more number of times, you want to use the shortest bit string to send this. Shortest possible bit string to send this message. Then you want to use the longer bit strings to send less probable messages, because you will then send this less number of times. So that would not add on to the total length. So the average code length that we define is probability times the number of bits in the code word for that message, right? For encrypting that message, right? So we want to use shorter bit strings for more probable messages and longer bit strings for less probable ones. So for example, I could say the bit string for A is 0, right? That is, I'm transmitting 3 messages, A, B, C, and I'm picking some bit strings like ones and zeros to send this to Bob, right? So I'm going to send it as some pulses or some bits. So A is more probable, so I'm going to pick only like 0. Or I could pick 1, whatever, 1 string, right? And then B and C are less probable, so then you can pick 2 strings for them, 1, 0, and 1, 1, right? So, or you could put 0, 1, 0, 0, whatever you want, but you can pick two strings. So that would be the optimal length would be 1.5 bits, which is same as the entropy, right? So that's the average thing. The code is optimal. That is, it cannot be compressed less than whatever is the entropy. You cannot compress that below this 1.5 bits, right? So now this is whatever Alice is sending, like to follow up with Shubhanshu's question, now we are assuming that whatever Bob is receiving, ideally it is correlated perfectly with what Alice is sending, right? But that need not be true, right? So let us say Bob is receiving messages denoted by Y, and those values take little yn, and his probabilities have qn, right? So then Bob reads the messages and he gains information, and that information we are going to quantify with h of y. So h of y is on Bob's side, h of x is on Alice's side, right? So to quantify how much information Bob actually learns from whatever Alice is sending, we consider the joint entropy, right? Joint entropy is, we define it as h of xy as minus sigma probability of joint probability of xj yn, that is Alice sends message xj and Bob receives yn, whatever message, right? And we hope that these are perfectly correlated. If it is a good channel that has no noise, then yn is perfectly correlated to xj, right? That is, whatever she is sending, you are getting exactly that. If she sends 1, Bob gets 1. But if there is noise, that need not be true, right? So that's why we are giving it in general a different symbol. And again, log of the joint probability distribution xjyn. And then we are going to sum over j and n, right? That gives us the joint entropy of x and y. So the conditional entropy, right? It measures conditional entropy, meaning now let's say Bob has received the message and Bob has made a measurement, right? And he may learn certainly about, if it is perfectly correlated, he learns it with perfect certainty that this is the message, then well and good. But there may be, whatever, due to the noise or whatever reason, right, you don't get the full information. You still have uncertainty, whether that is due to noise or due to some other reason, we do not know. But that means that yn is not perfectly correlated with xj. If yn is perfectly correlated with xj, right, then Bob learns exactly whatever Alice sent. But if after making a measurement, Bob does not, is still uncertain about what Alice sent for whatever reason, we define a conditional entropy, that is h x y with a bar in between, which is the joint entropy h of xy minus whatever is Bob's entropy. So in an ideal scenario, this conditional entropy, we will see later that it is minimized, right? So if x and y are uncorrelated, that is whatever Alice is sending, Bob is receiving something that is not at all related to x at all, then we can define the joint probability distribution of xj and yn as probability of xj and probability of yn, because they are not correlated with each other at all, right? They're independent of each other. Probability of xj is pj, probability of yn is qn, right? In that case, you can see that h of xy is simply would be equal to minus sigma pjqn log of pjqn, right? So then you can write log AB as log A plus log B, right? And then you can separate them out. So you can write h of xy as h of x plus h of y, right? So in that case, they're uncorrelated. The joint entropy is completely additive, right? There is no correlation. In that case, what happens is the conditional entropy in that such a case, in uncorrelated case, what would be the conditional entropy? That would be h of x, h of xy minus h of y, right? So you just get that to be simply h of x, right? Now, if it is perfectly correlated, so if y gives no information, about x, then h of conditional entropy h of xy is simply h of x. That is, Bob's uncertainty about x is unchanged. That is, he doesn't know before he receives the message, he doesn't know what Alice is going to send. Now, if it is perfectly uncorrelated with the his whatever he receives is uncorrelated with Alice's message, right? Then he is not going to learn anything after the measurement also. So the entropy still remains h of x. But if y perfectly determines x, right, then we would expect the conditional entropy to go to 0, because now we have perfectly learned what it is. There is no uncertainty anymore, right? Then in such a case, then the joint entropy would just simply be h of y, right? And the conditional entropy would be 0, because now conditional entropy is based on the correlation, right? So here you see that it is based on joint entropy minus whatever Bob's entropy is. If this itself is h of y, that is, there is perfect correlation, then there is no uncertainty after the measurement what Alice sent. You have perfect correlation between what she sent and what is received, right? Were you able to follow so far? Any questions? So h of x comma y is joint entropy. H of x is Alice's. H of y is Bob. And h of xy is the conditional entropy. And this tells the correlation between what Alice sent and what Bob received. If xj is perfectly related to, let us say Alice sent xj and Bob received exactly that message, then the conditional entropy is 0, right? On the other hand, if Alice sent something and what Bob received is uncorrelated, then the entropy of Bob, which is h of y, doesn't reduce at all. H of x, which Alice sent with, that doesn't reduce at all. If y, measuring y gives no information about x. Any questions? Are you guys able to follow me? Okay. I need some validation from you guys in terms of the material, because I don't know if you're understanding or I'm okay. There are some yeses, 3 yeses. Okay. Okay. Thank you for acknowledging. Please, are there any material related questions? Okay, the reason we are discussing this is we need to understand the channels. We need this kind of little more basics of the information theory. That's the reason why we are doing. So now we are going to determine one more. We define joint. Joint is comma, conditional is the bar, and now we are going to define mutual, which is, you know, this colon, and that is, so mutual information is, it is h of x plus h of y minus h of xy, right? So or you can write even the other way around. You can write h of xy as h of x plus h of y minus h of x is to y. Right? That is like, you can imagine, like, you know, if you have done set theory, right, you have two sets, right? And you want to count, you know, you don't want to double count this part, right? So the mutual information is what you exclude, right? So that's what we mean by mutual information here. So that is the mutual information entropy, right? And we can redefine that in terms of conditional entropy. So joint entropy, conditional entropy, joint entropy is you know, together how much they have, right? Here we have defined h of x plus h of y. Conditional entropy is how much uncertainty remains after measurement. Mutual information is how much they share, right? So now let's say If X and Y are perfectly correlated, then the mutual information that they share is the same thing. That is, whatever Alice has, Bob also has, right? So information sent by Alice can be completely be recovered, right? Now, so far we have not considered the effect of the communication channel. So this is again, we are saying Alice is sending to Bob, so or somebody is sending to somebody else, but in general, it is nobody has to send it to anybody. Like it could be that I prepared drawing a parallel between what we discussed in quantum, right? Suppose I initialize like QC dot some circuit X0, right? So this itself I could consider as a channel, meaning that I am initializing a qubit, right? And I'm applying a gate and one, right? So I can sort of think about this as Alice and this as Bob, right? So then if Bob gets one, that means that and you know that there is a NOT gate, then that means that you know that this side it is zero, right? So I can define information like this, like in terms of when we say Alice and Bob and eavesdropping, that need not be really people just sending information to each other. Even the processes that we are describing, any step, any two endpoints in the process, we can consider as Alice and Bob, and any effect of the noise, we can consider as Eve, right? So it's not really people exchanging information, but it is like part of the process, different steps in the algorithm. Any 2 points, I can take that before the gate and after the gate, I could consider as Alice and Bob, right? And so I can apply all this to that. So far we have not considered Eve. So Eve has to do with the channel, right? We considered that there is no eavesdropper, there is no noise. Noise is one type of eavesdropper, right? So it is not that somebody is trying to steal information. We just describe it in those terms, but whatever principles we are developing here are also applicable to just noise and other things, right? So the communication channel, right? We define the channel capacity as how much information can be transmitted per use. So remember that we said when Alice has messages x1 to xn, right? She can send one message per use, right? One message per use. That is, you are performing one computation per use. Again, this is not literally Alice sending message to Bob. It could be we are performing some gate operation on some qubit, right? That could be the channel. The gate operation is the channel. The initial qubit is Alice. The end qubit is Bob. And what we ideally would want is perfect correlation between the result and the input and the output, right? So the key question is, can Bob reconstruct Alice's message from the received one, right? That means, like, for example, go back to this NOT gate example. So if I apply NOT gate and I got one, right? So I'm going to get only whatever result I get at this end, right? I get whatever I got here, right? If I know only that, and I know that NOT gate is applied, then I would say that, okay, Alice sent me zero. That is, the initial qubit is zero, right? But the question is, what we are asking is that, is there any noise in between? That is, did Bob get the right message? That is, if Bob applies X inverse on whatever he received, right? Then does that match with whatever Alice sent? You see? So if this is true, you should get one, right? If this is not true, like let's say Bob got, instead of 1, he got 1 over square root 2, 0 plus 1, then that means you cannot reconstruct whatever Alice said, right? So if the messages are perfectly correlated, then the conditional entropy is this. So from the Shannon's theorem, the h of x is, you cannot compress whatever is h of x. That is, you need to use those many bits at least of information per channel use if you want to send. So if I want to send like two states, if I have two states, 0 or 1, I have to use at least 1.5 bits, right? Or 1 bit, right? So if I have two states, I could send 0 or 1, each with probability half, right? Then I need to use at least h of x bits, that is, minus pj log pj and j summed over, right? That will give me 1. So I need to at least use 1 bit of information to send that, right? So we're not going to prove this, but Shannon's noisy channel, when you have noisy channel, then this is not the case anymore. In a noisy channel, what you have to do is you have to pick the max entropy, max mutual entropy, that is h of x is to y, right? That is the mutual entropy, that mutual information that we define, that is h of x plus h of y. So we are not going to prove how this came about, but what we are saying is that whatever is the maximum entropy, you pick that, not the, for example, if I go back to this one, so if I want to send this here, 0 here, right, the entropy is 0. Here, the entropy is 0. So if I want to send it over a noiseless channel, right, then I don't need to worry. I can just send it whatever that is. But if I want to send it on a noisy channel, I must necessarily pick the maximum here, right, and use those many bits to send my information, right? That's what the Shannon's noisy channel theorem is basically telling us. So sometimes this is expressed as not per use, but as bits per second. That means you multiply per use with number of channel uses per second, right? So you can define a transmission rate as number of information bits transmitted by number of channels used. So for a code of length n, you get this thing. So if your transmission rate is less than the number of bits required to reliably transmit the information, right? Then if your transmission rate is less than the maximum entropy, then you can reliably transmit information. But if your transmission rate is more than that, then that means you end up losing something and you cannot transfer the information from one side to another side. So the maximum, this determines, in other words, the maximum entropy determines how fast you can send. You cannot send faster than that. If you send faster than that, then you're going to end up losing information because the channel is noisy. We're not talking about noiseless channel. That is, if I try to perform the computations very fast, right, then I'm going to end up getting errors. There is an optimal rate at which I can perform the computations. If I perform any faster than that, then I'm going to get errors. So there is a minimum time I need to take, and that is determined by the maximum entropy based on my information. So that is in case of a noisy channel. If there is no noisy channel, then we don't need to worry about the maximum rate, because in a noiseless channel, basically there is no noise, right? So reliable transmission is always possible. Any questions so far? Are you able to follow me? So far what we discussed is classical information. So in case of, okay, there's some question. Okay, thank you guys. So in classical, we said that whatever Alice has, she has definite states, right? We said Alice has some information. We were saying that Alice has some information, some messages x1, x2 till xn that she can send. Now, when it comes to quantum information, these are replaced by the density matrix rho, right? That is, Alice has these states which can be represented by rho 1, rho 2, rho n. Each of this is a density matrix. Are you with me? And then recall that we can do a general convex combination of these density matrices, which means I can add them with probabilities and not probability amplitudes. So in general, I can express rho as sigma j, pj, rho j, right? So just like how we defined information entropy, Shannon's entropy in case of a classical one, right? That is x1 to xj with probabilities p1 to pn, right? There we defined information entropy on x as minus sigma j pj log pj, right? Here we are going to define s of rho over rho. That is, our rho is each message has a probability pj. Each state has a probability pj. right? And each of these states is a density matrix. That is, we have this much probability that she will send this state, the density matrix corresponding to this state, right? And again, the reason we are considering density matrices and not kets is because you may not be able to represent a mixed state with kets, and you cannot do a convex combination with kets, right? That's why we are doing density matrices. So we want, again, this entropy should not change based on the, if I change the basis, the entropy should not change, right? So that's why again we are taking trace, right? We're taking trace rho log rho, right? And that would be same, you can show that that is same as minus j pj log pj, right? So this von Neumann entropy measures, it is just like Shannon entropy, except instead of messages classical bits x1 to xn, I have density matrices rho 1 to rho n, right? If I know exactly which state she is sending, that is, if I know that she prepared pure state 0 and the density matrix that I am getting is like, let's say 1001, whatever matrix, then if I know for sure, then that means Pj is 1. If the probability is 1, you're certain about it. And when you're certain about it, the entropy is 0 because there is no uncertainty. So if the rho is maximally mixed state, then what you would end up getting is that you would get that to be S to be log of the dimensionality. So if it is, recall that for a maximally mixed state, we saw that irrespective of the basis, we would get that rho of for a maximally mixed state, we got as I by 2. We did this when we were doing density matrices. I hope you recall that. Like we did for a mixed state, we showed that it is I by 2. And that's how we defined the mixed state there. So if it is maximally mixed, then you can show very easily that you should get that to be log of dimensionality. This I by 2 is for dimension 2. In general, it would be I by d. So you would get maximal mixed entropy as d, where d is the dimension of the space that we are using, right? So if we choose to express our rho in some sort of a basis, right, which we can do from, we discussed the spectral decomposition theorem when we were describing density matrices, and that's why we took entire lecture to do density matrices, right? So that guarantees us that we can find some basis where we can expand this into rho into some sigma j, eta j, jj, right, where eigenvectors and eigenvalues, right? And we have the probabilities sum up to be 1. Then you can show that the von Neumann entropy simply becomes whatever is this nj, right, or pj, whatever you want to call it, eta j ln eta j, right? So von Neumann entropy is identical to Shannon entropy in that sense, except it is on density matrices instead of the classical bits. Okay, now let's ask the same question. Again, when we talk about Alice and Bob, I want to reiterate, this need not be real people like Alice is sending to Bob. It could be, I'm preparing, state preparation, could be Alice, right? Some gate could be eavesdropper Eve, and measuring device could be Bob, right? So when we are talking about that, this doesn't have to be about exchanging some codes, right? So when I talk about Alice and Bob share a Bell state, that means state preparation and measurement are trying to do the same thing, right? State preparation is making a Bell state, and the measurement is also going to happen on the same state, psi minus, right? So what we want to do is find what is the reduced density operator for each of them, and what are the probabilities for local measurements when I measure it here, right? And when I project the system onto orthogonal states of Alice, that is the whatever is at the step 1, phi 1a and phi 2a. These are whatever, these are two orthogonal states that some basis that is being used at one side, on Alice's side, right? So we want to find the reduced density operator, right? So how do we do that? Recall that we have, let's say you have two things. So you have a direct tensor product there. right? So first we can write the Bell state psi minus as 1 over square root 2, right? You have 0, 1 and minus 1, 0, right? So then we can, this is the state that Alice and Bob are sharing. So then we can write the joint density matrix rho AB, right, as psi minus, right? So if I pick the four state bases 0, 0, 0, 1, 1, 0, and 1, 1, right? I can then express psi minus as 1 over square root 2. There is no 0, 0, so the 0, 0 component is 0 in this basis. 0, 1, I have 1 over square root 2, so that is 1. 1, 0, I have minus 1. And 1, 1, I do not have, so 0. So this is my psi minus. So if I want to compute the density matrix rho AB, I can do 1 over square root 2, 0, 1, minus 1, 0, and another 1 over square root 2. So I would just square this, 0, 1, minus 1, 0. Right? Are you with me? And then from there, I can compute my 4 by 4 density matrix because I have 4 basis states, right? Which would, you can confirm for yourself that the joint density matrix for the Bell state that they share would be this. Are you following me? So what we derived is the first part. Alice and Bob share a Bell state. We want to first derive the joint density operator, the density matrix. So we identified psi minus, expressed it in some basis, and we did this. So whenever you get some matrix, density matrix, make sure that it sums up to 1 along the diagonal. It does. You have 1 plus 1, 2, and it is divided by half. So you do get this thing, right? You do get the trace of rho of AB to be 1, right? So our base is then, right, the reduced operator means that you sum over. So if you are trying to find out the reduced, so if I have rho AB, that is, let's say, rho A and rho B, right? If I want to find just rho B, I have to sum over rho A, right? In other words, if I want to find probability of Y, I sum over X of probability of XY, right? So I have to sum over A to find the reduced density operator for Bob. So we figured out what rho AB is. We calculated that. And we are given the basis for Alice, right? Alice basis is 0A and 1A. So 0A and 1A. So then what we are going to do is we are going to simply to get rho B, the reduced operator for Bob. What we are going to do is we are going to sandwich between 0A, rho AB, 0A. So I'm summing out whatever is Alice's states, rho AB, 1 Alice. And this rho AB is what we are writing as psi minus, right? Psi minus. And so if you compute that, then what you end up getting is, a maximally mixed state. That is, here, the state is entangled, meaning I cannot tell whether the first bit is 0 or second bit is 0. It is maximally mixed. I cannot tell whether the probability of finding the first bit to be in 0 state or the second bit to be in 0 state is half. Recall that when I have probability of half, I reached maximum entropy. So for this entangled state, I have reached maximally mixed state. You could have done the same thing for Alice also. That is, you could invert the situation that for example, you could do rho A, and then also you would see that even if you summed over B states, that also would give you a maximally mixed state, because in the entangled state you have, it could either be that first bit is 0 or the first bit is 1, or second bit is 1 or second bit is 0, both equal likelihood. Are you able to follow me? So we have maximum probability there. Maximum entropy there. Did you follow the example? Any questions? Are you understanding me? Okay. Which part, Anuradha? How it is symmetric? Yeah, I mean, so let's say instead of row A, so instead of row A B reducing to row B, let's say I want to reduce this to Alice's row A, right? The way I do that would be sum over B. So I would have to do 0 for Bob, row A B, whatever is 0 for Bob, right? Plus 1 for Bob, row A B, right? 1 for Bob, right? And that would give me exactly a similar matrix like this. Instead of for Bob state, I would get Alice states, because this has row AB is nothing but psi minus, right? So if I plug that in, it is exactly the same. So instead of having Alice's summed over, you would have Bob summed over, and you get again a maximally mixed state. That is, it doesn't matter, like you have the state in an entangled, the state is entangled, meaning qubit 0 and qubit 1 have equal likelihood of being found as half, right? That's why it gives you maximum entropy. I hope that explains. Okay. So now again, we are going to define joint entropy and conditional entropy, just like how we define for the case of classical bits, right? Recall, we defined h of x as minus sigma j pj log pj, right? And h of xy we defined as let me just go back. I wrote this somewhere. So h of xy we defined as joint probability h of xy minus h of y. So you can see I'm putting it in the yellow box here, right? So the joint probability we defined as this, and then this is the h of xy is the joint probability. So rho of AB is the joint one here, right? You have joint entropy. And so you can define a conditional entropy where you subtract Bob's entropy, just like how you subtracted h of y. And you can also define a mutual information again the same way, like how we defined previously, right? So these are in general the expressions for classical to quantum systems. So now that we have defined these things, we can now tackle what kind of channels induce noise and how that noise looks like, right? So measurement on any one subsystem influences the total entropy. Because if I learn about one qubit, let us say in the entangled state, if I measure Q0 to be 0, then I'm assured somehow that Q1 is going to be 1 overall, right? That's what it is saying, that if I learn about one qubit, then I gain information, entropy is reduced, right? So we can in fact compute the joint entropy, right? Joint entropy would be 0, right? Because you can express this as psi minus, right? So you can express this as psi minus psi minus. If I know with definite this thing that it is 0, 1, then you can say that for a pure state that is 0. If you have a reduced state which is maximally mixed, then you have maximum entropy, so you have 1. And the conditional entropy would be negative, right? A negative conditional entropy implies that you have perfect entanglement, right? That is perfect anti-correlation. So when you have -1, that means that if you have 0 on one side, it is perfectly anti-correlated on the other side. That is, you get 1 on the other side. That's what it means. If you have S of rho AB to be 1, right, then that means perfect correlation versus perfect anti-correlation, right? So although each subsystem, that is, I do not know whether qubit 1 is 0 or qubit 0 is 0. If one is known, then the other is, the uncertainty about the other goes down. So although each subsystem is maximally uncertain, the total joint system is pure. meaning their correlations are carrying all the information. That means between the correlations, we can get the total system. S of row B, row AB is 0. I hope you are able to make sense of it, right? So we can talk more about this in tomorrow's lecture. And then what we are going to do is we are going to sort of say that we prepare a qubit in some state, and then we are going to begin introducing decoherence. And the idea is to see how can we represent this decoherence? How can we now introduce a noisy channel? And what happens to these entropies when we introduce a noisy channel? And by modeling these noisy channels, we are going to be mainly be modeling two noisy channels. One noisy channel is called dephasing, and another is called depolarizing. Right, this dephasing and depolarizing that we will see tomorrow, right, will basically be related to how they change the. So the depolarizing channel takes any qubit state and makes it maximally mixed, right? That is what the depolarizing channel does, and what dephasing channel does is it makes it diagonal. That is, it makes the off diagonal, whatever coherences are in the off diagonal elements, it removes all those things, right? It's also sometimes called phase damping, right? And we are going to talk about how these quantum channels can be expressed. And then we're going to send this out, and then I have some actual examples that we can run on QPU. And like I said, we don't have to consider Alice and Bob as two people, but we can consider as state preparation or measurement or gate and measurement, and then use these channels in between. That is, I can introduce this noisy channel and try to model how quantum noise comes into picture, which would be useful for error mitigation and error correction. So tomorrow morning we will cover tomorrow afternoon we'll cover in the first lecture the remaining part of quantum channels. And then following that, we will cover quantum key distribution. Specifically, we are going to do something called the BB84 protocol. And so we will also do, again, hands-on on actual QPU with BB84 protocol. And we will try to implement some sort of a noisy channel in BB84 protocol. That is, we will introduce Eve, who is going to eavesdrop or introduce noise into the system. And we will see how that is different between classical information versus quantum information. And then we'll try to digest that in terms of ensemble interpretation, what all of this means, and then move on to quantum algorithms from there. So that is what we have in the upcoming lectures. We have 2 days left. So tomorrow we will try to finish quantum channels and a bit of quantum key distribution in the 2 lectures, and hopefully get introduced to quantum algorithms. And if time permits, we probably will cover Shor's factorization algorithm, if time permits, on Friday. And then in the final lecture, what I would like to show is, so far we have done only like simple circuits, but there have been some studies where they have used a real quantum computer for predicting, let's say, protein folding structure or other relevant examples like quantum machine learning. So I would like to just give you briefly what is being done and what is emerging, and hopefully you can use those to kind of go further. And in the next 4 lectures, we will be basically be ending whatever we have. And if you need any other thing, please come up with more questions that you may have, because we have only 4 lectures left to address. I would be happy to address your questions after the thing through email, but I wouldn't guarantee it, because both Dr. Gargi and I have very active research groups, and we do not know how much time or how much delay may be there in between answering your questions. So it would be best to bring your questions, as many questions as you have, for the next 4 sessions, so we can discuss and answer your questions or point you in the right direction to the best of our ability. There seems to be a question Sir, I lost my network. Could you repeat again what I missed? Okay. I'm sorry, Anuradha. I basically was saying that we will repeat this again tomorrow. So, hopefully you will be able to cover that tomorrow. I have just gone over what we are going to cover. So I'm sorry that so if noiseless channel, then we can process information faster. Yes. So if you have noiseless channel, then you don't have to worry about the but the noiseless channel is like saying frictionless thing. You cannot create it. There is no noiseless channel, right? It is just an ideal situation, right? So it's like saying that if there is no friction, will I not get, like if I push something, then I don't need to keep applying force anymore. It's just going to have that momentum forever, right? It is like that. But if it is there, friction is there, I push it, it's going to stop sometime. So does it mean we need to improve our gates for faster information processing? That is the point, that the friction cannot be removed. So what we have to do is we need to improve our gates in the sense that more than improving the gates, what we would like to do is sort of model this. So we can first, instead of running on the real quantum computer, I have the ability to first run on a noisy simulator. And if I know what kind of, like, let's say if I'm applying a particular gate and I apply that particular gate several times, that gate itself is like a channel. And so if I can figure out what kind of noise, what kind of dephasing or depolarization it is inducing, then I can apply the inverse of it, right? And sort of do the error correction. So that's where we are going to use that channels. I hope that answers your question, Subhanshu. Okay. Any other questions? Okay. So we'll stop here for today. And please bring as many questions as you have for the sessions in the next 4 sessions. And make the best use of whatever sessions are left. Thank you.